today we will have the slab for our discussion. So there are three types of slab as of today's construction. First is the one-way slab. It's a slab supported by two beams on two opposite sides only, or by four beams on all four sides, but with M equal to or not, or that is less than 0.5. So normally for one-way slab, this is for one-way slab, normally your M is less than 0.5, and you only consider the short span in designing. Okay, so where your M is equal to the short side or the short span divided by the long side or the long span. So for example, this is 4 by 3, so this is 3 over 4, that's equal to 0.75. Therefore that is not, or one-way slab. So it should be, this is 1, and this is 4, therefore that is 1 over 4, so that is equivalent to 0.25, that is less than 0.5, therefore that is one-way slab. Okay, so for the two-way slab, a slab supported by beams on all four sides with M greater than or equal to 0.5. So if ever you have a dimension of 2 by 4, so that is 2 over 4 equal to 0.5, so therefore that is two-way slab. Okay, so that's how you decide your slab, if that is one way or two way. It's because of in solving your M, and sometimes in the problem it is stated that it is one way or it is two way, but in our case, I'll just have you design only for one-way slab, since two-way slab, for two-way slab, this is not just a not so complicated problem, but there are consideration for discontinuity case. So discontinuity cases, it's for example for this one. So in this portion, there are no slab considered, and this for this one, it's have a slab, so therefore you have discontinuity here, and this is continuous, and continuous. So you have the table for discontinuity cases. And then for the flat slab, it's a slab resting directly to column and without beams. So normally for flat slab, the beams already incorporated to your slabs. Okay, so for flat slab construction, you have this in other buildings, so they don't have beams automatically from column, they already connect the slab. So that is the flat slab construction. So in the Philippines, this is what do you call that, this is discouraged. It's because of its risk in construction, or for the safety of the public, since once the slab collapse, automatically the column collapse. Unlike the two-way and one-way, you have the beams from slab loads that is transferred to the beams, and the beams to column. So in that case, if the slab collapse, you have the beam that supports the slabs. Unlike for flat slab, you have only the column. So once the slab fail, so the column fail. Okay, so let's have only one-way slab in our computation. So for two-way and flat slab, maybe for in your case for architecture, for the computation for two-way slab, maybe we don't have enough time for the calculation since we have the stair slab and stair slab columns and footing topics. Maybe for if we have time we can discuss the two-way slab, but as of now we will have only a one-way slab. For one-way slab, so as what I have said, it should be that M is less than 0.5. So for example, you have this slab, considering this is 4 by 1 or 1.5, so you will consider your short side. So for the long side, you will just consider 1 meter strip. Okay, so this is the main bar of the one-way slab, and this is the temperature bar of the one-way slab. So considering the 3D section, you have the short side now, so it considers as the long side, but it's the short side with the whole slab. Then you consider the 1 meter strip, and you have the thickness. Okay, and then you have the spacing of the main bar. Then the thickness is from the top to bottom of the slab, and then you have D and the cover. So T is the slab thickness, that is equivalent to D, or the effective depth, plus the cover. Okay, then from the Aci Code Consideration, that is American Concrete Institute Code Specification, so the minimum main bar diameter of slab is 12 mm, and then the temperature bar is 10 mm. The minimum clear cover you have 20 clear cover, so minimum you can have 30 up to 60, so up to 60 millimeter if you have a thickness more than 100 millimeter. So it's up to you how to you design your structure. And then for the minimum slab thickness, normally for the minimum slab thickness, you have these formulas. Okay, for cantilever slab, so meaning cantilever, so you have the beam and then the slab. This is the cantilever slab. Then you have the simply supported, so you have the beam, then the slab, then one end continuous, so you have the slab, so at this point the slab is continuous, this one. So from one span to second span, that is continuous. Then both end continuous. For both end continuous, you have this one. So if you consider this span, or if you consider this slab, so for its ends, that is continuous. Sometimes you are given plan, considering the slabs. So maybe some of you already know how to draw framing plans. So for example, this is the slab considered, and this is the short side and the long side. So for this slab, this is for one way slab. So for this slab, this is continuous at both ends. Okay, so for this slab, this is continuous for one end. Okay, so you consider the as a slab as to design where it is located in your framing plans. Okay, so you have this formula. So in this case, you have the multiplier. In some cases for the Aci code, since for the Aci code and NCP code, normally every year or every 5 years, they updated the codes. So in some case for your notes, the multiplier or the minimum thickness of slab is considered is only this one. So the same as this one, but they don't have the multiplier. So you can use that. You can use this minimum thickness calculation, or you can use that or this calculation. It depends on how you design or how you interpret the design problems. Okay, so if you use this, you can have the computation, since this is just solving the thickness of the slab. So maybe the difference between this calculation, this one and this one, is more likely 20 mm. Okay, so you can use this or you can use this calculation in your notes. Since I use this notes again, so I will use this calculation in my problems. If you use this note, so you can also use this computation or formula for your computation. Okay, so by the way, for the effective depth, I have here the diameter. So in our case, for this problem, that is plus the diameter of the bar, main bar, divided by 2. Okay, and then the minimum thickness of slab minimum is 75 mm. Okay, so but take note, in these formulas, if you have Fy equivalent to 414 megapascal, so the quantity of this multiplier is just equal to 1. So in this case, you have this formula, the same formula as this one. Okay, but if your Fy is 414. Okay, so next is the spacing of the main bars. It should be the spacing is greater than 100 mm or equal to 100 mm, but less than 3 times the thickness, or 450. So if you compute your S equal to 400, okay, and then you check this minimum or spacing of main bars, and your thickness is just 100, so your 3T is equivalent to 300. So you will use 3T for your S. Okay. So next is the spacing of temperature bars. So your S should not be greater than or equal to 5T or 450. Okay, so to solve for S, if that is 500, so therefore you have 450. Okay, so it depends in your calculation also. If you have a greater S than 3T, a greater spacing for 3T and 5T. Next, number 7 is the area of shrinkage and temperature bar. So you will have to use a temperature bar always, since the placing of the reinforcing bars is this one. So you have the main bar, the main bar, and then the temperature bar or the shrinkage bar. Okay, so normally this is called bent up. So in construction, we will not use this. Normally we'll have to use the cut-off bars. Cut-off bars meaning you have to cut at this point for the top bars, and then you cut again for the bottom bars. So that is called cut-off bars. So your reinforcing bars is cut, so at this point. So for the section, you have this slab. So you have these top bars, and then you have these bottom bars. That is for the cut off. If you have the bent up, so for bent up, this is continuous. Okay, that is bent up bars. So normally during construction, we will not use this. It's because we don't have the machines and the manpower or the workmanship of the workers. So it's not advisable to use bent up, but it is in the code that it should be used so that you have the structure stronger than the cut-off bars. So if your workers, you have the limited time, so you just use the cut-off bars. So it's the same calculation, the same number of bars top and bottom, but you just have to cut the reinforcing bars. Okay. So you have the shrinkage or temperature bar area, AST, is equal to the rho. So normally the rho is specified in ECP specs. So for 276 or 275 megapascal and 345, so you have the rho of 0.002. If that is 415 or 414, that is 0.0018. And for Fy greater than 415 or 414, that is 0.0018. So since in the 2015 code, you will have to use, if that is 12 mm, so your Fy should be 276 megapascal. If that is or below 12 mm and below, then 16 mm above, you will use Fy equal to 414. Okay, so since the NECP code always updated the code as of now we have so many occurrence of earthquake, so they will have to increase the strength of our structures. Okay, so take note that the rho should be greater than 0.014. Okay, if your rho computed here is just equivalent to 0.0012, so you will use this rho to solve for the area of the temperature bars. Okay, so in this in ACI code or the NACP code, you have the required AST. So this is for the shrinkage, area of the shrinkage. And for the steel cover, if that is permanently exposed to the ground, it should always have a clear cover of 75 mm. Okay, so normally that is outside the building, so you can have 75 mm cover. Okay, so let's have some example.